Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And this hour, we're very glad to say that we have with us Dr. Neil deGrasse Tyson, director of the Hayden Planetarium, author of a number of great books, including Astrophysics for People in a Hurry, Death by Black Hole, and many people consider him the successor to Carl Sagan. He was recently the host of the National Geographic Cosmos series. So we're going to be talking about, well, the universe with Dr. Tyson. Okay, Neil, let me ask you a question about your youth. When you were a young guy, maybe 8, 10 years old, what started you off on this great journey to become an astrophysicist?
It was exactly that age, and it was a family visit to the local planetarium. And I think we all remember our first visits to a planetarium, because for so many of us, it was our first virtual reality experience, really. And you sit down, and the lights dim, and the stars come out, and basically the dome disappears, and you are sort of in the universe. So this happened to me at age 9, and I'm pretty sure the universe selected me, because I felt helpless in the allure of this boundless and endless frontier. And that local planetarium happened to be the Hayden Planetarium, where I now serve as director.
Okay. And then what steered you in the direction of, well, telescopes and reading about astronomy textbooks? Did you have a telescope as a child?
No, not initially. So I think many people's first encounter with sort of a magnified sky would be like binoculars. And I remember seeing the moon through binoculars for the first time. By then I might have been about 10. And what's interesting, I don't think people think about this much. If you look at the moon with your eyes, it's just the moon. When you look at it with binoculars, it is an entire other thing. You see mountains and valleys and craters and hills. So it wasn't just a bigger version of what your eyes saw. It was better. It was nuanced. It was textured. And I realized that if binoculars could do that, imagine what a telescope could do. So by the time I was 12, I got my first telescope, and it was a birthday gift. And my parents bought it for me. It was a 2.4-inch refractor, if you're into sort of amateur astronomy lingo. And with that, you can see the rings of Saturn, the moons of Jupiter, the weather bands on Jupiter. And if you project it correctly in the daytime, safely, you get to see sunspots. So I was totally into the universe, now with methods and tools of science, by the time I was 12. And about a year before that is when I realized you can make a career of this. I could be that as a grown-up, so that when grown-ups asked me, what do you want to be when you grow up, I had an answer to that annoying question, and my answer was astrophysicist.
Okay. Now, when people email you or meet you and they say, what should I do? Because I want to become an astrophysicist, too. Do you tell them to buy a certain type of telescope? What do you advise them?
You know, that's a good question, because my first thought is not to buy them for them to get a telescope. And I don't have a good answer for why that's not the first thing I say. Generally, depending on how old they are and where they are in their a trajectory of education, because my answer would be different in each case. What will be included in my answer is to do all they can to embrace math, because math is a language of the universe. And I say this often, where if you want to go to China, you learn Mandarin, perhaps, or you want to go to Spain, you learn Spanish. France, you learn French. You want to commune with the cosmos, you learn math. Because it's remarkable that it's true that the universe talks to us in math, even though we invented math out of our head. This is a remarkable fact, but it's true. So I get people to get comfortable with math, and so some books I would recommend that treat math as sort of a fun thing that you would apply to your life. And then you take physics. there's no understanding of astrophysics without physics. In fact, there's not much understanding of anything in the world without an understanding of physics, as I'm sure you know. Yeah. So, because, for example, there's no understanding of biology without chemistry, and there's no understanding of chemistry without physics. If you look at I have one of these, a chemistry book from the 1800s, before quantum physics was developed in the 1920s. You look at a chemistry book, it's almost like a cookbook a descriptive cookbook of what happens when you combine different chemicals. You put this to 3 parts this and 2 parts that, this happens, and it feels warm. You put these together, it feels cold, and you put these together, it changes color. And there's no real understanding there. And in physics, we figure out why a periodic table of elements exists in that shape, in that form. And that comes from quantum physics. Now that blows the lid off of chemistry, and now they can talk about molecules binding and electrons and energy levels and transitions and all of this. So that's also part of the advice I would give. I guess the telescope advice would be to help you sustain that interest. If the going gets tough in your classroom, or if you start losing your passion, you just take a peek through a telescope, and that will reignite any flame that you ever had.
Okay. Now, I remember when I was a kid reading about astronomy, we were all focused on the planet Mars, because perhaps there were Martians on that planet. But I understand that we haven't found much life on Mars at all. So what's going to happen when our astronauts reach Mars sometime in the 2030s?
Well, so just to be, in all fairness to those who imagine life on Mars, Mars, has captured our imagination at least for, 130 years or so. When Percival Lowell, back in the turn of the previous centuries, 1800s to 1900s, had Mars as quite an object of his fascination, and he was intrigued, for example, that Mars was tipped on its axis like Earth, and Mars has polar ice caps like Earth, and these polar ice caps shrink and grow in response to seasons. So when you start seeing this, you say, oh my gosh, there's got to be life there. And so he went a little overboard in his imaginations about life, but his books triggered...
Okay, Neil, we have to take a short commercial break.
Okay.
But after that, we're going to jump right into the planet Mars and the moons of Saturn and Jupiter. Welcome back to Science Fantastic with Professor Michio Kaku. With us today is Dr. Neil Tyson. Many people think he's a worthy successor to Carl Sagan. He was the host of the National Geographic series called Cosmos, author of a number of great books, including Astrophysics for People in a Hurry and Death by Black Hole. Well, Neil, let's talk about the planet Mars. What do we know about that planet?
Well, just before we broke for commercial, I was offering the transition between Percival Lowell, who was an astronomer who had a really good telescope on a mountaintop in Arizona. He was wealthy, of the New England Lowells, so he had money to build an observatory. And guess what the observatory was called? The Lowell Observatory. So he studied Mars deeply, but his imagination went beyond the data because he really wanted there to be life on Mars and wrote about the possibility and the likelihood of life. In fact, he really thought he was observing canals on Mars, channeling water from the ice caps to cities. So he drew these in his books. This triggered the imagination of H.G. Wells, and H.G. Wells then writes War of the Worlds, where Martians are... This was directly inspired by the observations of Percival Lowell. And so since then, we've imagined peaceful Martians, evil Martians, but you're right, there is no life, not on the surface of Mars, at least. It's a wholly inhospitable place. No shielded ultraviolet rays, such as we have on Earth, and ultraviolet is damaging to complex molecules that you would need if you were going to have complex life. And so there's still hope that if there was ever life on Mars, because Mars has tremendous signatures on its surface from the action of water. There are dried, meandering riverbeds, floodplains that all dried. There are river deltas, all dried. Mars once had liquid running water on it, and every place on Earth where we have water, we find life. So we are still looking for evidence of life on Mars. If not on the surface, maybe deep beneath the surface. Could be microbial. So Mars is the center of everyone's attention in planetary exploration.
Okay, well, on Science Fantastic, we've had a number of scientists, including Dr. Zubrin, who believes that we should terraform Mars. That is, take Mars and change it into a Garden of Eden. Inject methane gas to create an artificial greenhouse effect. Satellites around the polar ice caps to melt them with sunlight. But, well, what are your thoughts? This is not going to happen anytime soon.
Well, but you got to give people space to dream that way. We do look at what else we do to our environment. We change the course of rivers. We level mountains to put freeways through. There's so much else we do that affects our environment, usually inadvertently harming it. But imagine if there was an entire frontier of altering our environment for the better and for the greater good. If we learned how to do that, and you could do that with Mars, this would be an entire other planet we could live on. And terraforming is one of the great new words of the last several decades, because its meaning is pretty obvious just when you unpack the two syllables, terraforming of it. I guess it's three syllables. Terraforming. And it's clear what that is. Now, here's my only rebuttal to that, is that often people say, let's help Mars become an Eden, and then we all move there, because after we trash Earth, we'll need a new place to go. And I'm thinking, that's not the right reason to do that. Plus, if you had the power to turn Mars into Earth, the power of geoengineering to accomplish that, then you have the power of geoengineering to turn Earth back into Earth. So there's no level of trashing of Earth that you could do that would somehow be immune to your power of geoengineering that would have otherwise turned Mars into Earth. So if you did it, it's because you really want to become a two-planet species. And I don't have any problems with that, and I don't think we're as far away as people think. I'll give it a century, perhaps. I don't think it's as far away as landing on the moon was to the Wright brothers. Let's put it that way, psychologically. So, yeah, I'm looking forward to it.
We had Carl Sagan on our airwaves, and he mentioned being a two-planet species because, quote, we live in a cosmic shooting gallery, unquote, with all these meteors and comets and space debris that could end life on Earth. So what are your thoughts about the argument that sooner or later we have to leave the planet Earth or die?
I think it's a spurious argument. So, in other words, I don't agree. So here's why I don't agree. If whatever it takes to terraform Mars and ship 1 billion people there so that we're a two-planet species, that's got to be harder than deflecting asteroids. I mean, if an asteroid's coming our way, is the right answer, let's ship 1 billion people to Mars, in this 9-month journey, or let's just bat the asteroid out or destroy it out of its existence. It's got to be easier to do that. It's got to be easier to invent the perfect antiviral serum to prevent us from dying from some future bug than it is to ship 1 billion people to Mars. So it's a matter of the practicality of implementing solutions. So sure, I would delight in the possibility of having a two-planet species. But the reason for doing that is not because we fear an asteroid that we can do nothing about. I just don't believe that we won't be able to do anything about it. So that's my sort of mild rebuttal to that argument.
Okay, well, the way that Dr. Sagan explained it on radio is, first of all, we need an insurance policy. Not that we want to ship everyone to Mars or even a huge fraction of the population, but just another branch of humanity as an insurance policy, because eventually the laws of physics catch up to you. 5 billion years from now, the sun is going to eat up the Earth, and we're not going to have a choice in that matter at all. But what are your thoughts?
Oh, completely true there. Right, because as the sun dies, it will expand, Earth will get hotter, and we will have to sort of planet hop our way to the outer planets of the solar system if we are going to survive that. But there's a bigger problem, and that is the sun is in the act of dying. So planet hopping farther away simply delays the inevitable. What you really want to do is find a freshly made planet orbiting a freshly formed star elsewhere in the galaxy, and presumably in 5 billion years we'll have that ability. If we went from the Wright brothers to boot prints on the moon in 66 years, seems to me we should be able to find a planet to move to in another star system. So, and by the way, the insurance policy, I can write an insurance policy that guarantees the destruction of harmful asteroids just as easily as I can write an insurance policy that says put us on 2 planets. So again, I'm more of a practical solution guy rather than a pie in the sky guy. And I know it's not as romantic to speak that way, but yeah, I mean we know we can destroy asteroids because Bruce Willis was evidence of this in Armageddon. So, but it's the scenarios, yeah, we would use nukes, we would use gravitational tractors. We have ways of thinking this problem through. There have been conferences on how to deflect asteroids or destroy them or render them no longer harmful. So we've got the thinking behind it. We just don't have the funding or the technology to accomplish it yet. But that could come if people have foresight. That's a big if, by the way, but yeah.
Well, other people point out that supervolcanoes could wipe out all of humanity because 70,000 years ago or so, Mount Toba erupted and probably destroyed 99% of all humanity, leaving only maybe 1,000 of us to repopulate the entire planet. And taming a volcano is a lot more difficult than deflecting an asteroid, right?
Well, so I don't know how to judge that. So I delight every time I hear your explanations about is it the Kardashev scale?
Kardashev scale.
The Kardashev scale, where, so imagine we were not as feeble as we are.
Okay, Neil, we'll talk about that after the break. Once again, you are listening to Science Fantastic. Our special guest is Dr. Neil Tyson. Many people consider him the successor to Carl Sagan. So stay tuned. Welcome back to Science Fantastic with Professor Michio Kaku. Well, Neil, before the break, we were talking about the Kardashev scale. Could you elaborate?
Yeah, I think your explication of it is like the best I've heard. But let me just sneak into one of those levels. So we're pretty feeble on Earth, digging natural resources out of the ground as our sources of energy, in this case, of course, oil. But imagine we had enough power of access to energy that all the ways Earth manifests energy, we could tap. So imagine a hurricane is ready to level a city, and you just go in with some kind of turbine that sucks the vortex energy out of that hurricane, and then you use that energy to power the needs of the city rather than watching the hurricane level the city. This would be a way of tapping the natural sources of energy that exist on Earth. The biggest source of energy, I think, by scale and by magnitude, are earthquakes. So imagine tapping the energy that would otherwise be shifting place on Earth, and you put that into some box, and now you can run your cities off of these boxes. Well, another one I'm thinking would be volcanoes, super or otherwise. You know, there's the Yellowstone supervolcano that's a little harder to tap that because it's so widespread. But imagine I'm just simplifying this just for the example, that you can tap a volcano the way we can tap a keg of beer. Here's this place, this volume, you tap a spigot in there, and then you draw out the energy that is otherwise contained in that volume, and you use that energy for other needs. Then the volcano never blows, because you're using that energy for other needs. So I will not sell short the future of the future creativity and ingenuity of engineers and scientists of our future for possibly being able to exploit all of that gurgling energy that's in the next supervolcano, thereby preventing a near or total extinction whenever that blows.
Okay, well, at Princeton, we have physicist Freeman Dyson, who says that once you become a Type 2 civilization, thousands of years ahead of us, capable of manipulating stars, then you are immortal. Nothing known to science can destroy a Type 2 civilization. But Type 1, he says, is still vulnerable. That is, what happens if you cannot tame a volcano? What happens if you cannot alter ice ages? And what happens if gigantic earthquakes and climatic disasters are beyond your control? Type 1 is planetary, which you mentioned, but some people think that Type 1 civilizations are, well, still vulnerable. But what are your thoughts?
I would wonder what we're vulnerable to, because if we can't quite tap the volcano and can't quite control the earthquakes, then we're not a type, was that type 1?
Type 1.
We're not a type, then you're not, planetary, then you're not really a legitimate type 1 civilization. You need numbers less than 1 to describe you. You're like, are you a half? My favorite is your declaration of us, what are you, 0? Type 0?
Great. Okay, Neil, let's take a short commercial break. And after that, I want to talk about 4,000 exoplanets that we've discovered orbiting other stars. Welcome back to Science Fantastic with Professor Michio Kaku. Our special guest today is Dr. Neil Tyson, author of a number of great books, including Astrophysics for People in a Hurry, Death by Black Hole, and of course he was the host of the National Geographic Cosmos series, and many people consider him to be the successor to Carl Sagan. So, Neil, what are your thoughts about the fact that we have discovered at least 4,000 planets orbiting other star systems? Don't you feel like a child in a toy store, just surrounded by all these toys that you can investigate?
I delight in this fact. And what's more impressive than that is we knew of no exoplanets as recently as 1995. So that's 23 years ago. And what I'd like to do is, whenever I give a public talk, I say, who here was born from 1995 onward? And maybe, 10%, or depending if it's a college campus or not. But if it's just the public, either some fraction of those hands go up, and I say, I will formally tonight knight you Generation Exoplanet, because they've only known life with exoplanets in the catalog. What's delightful about this is the sheer range of properties that we have measured of these planets. Big planets near their host star, fast rotating planets, slow rotating planets, planets in the habitable zone, the Goldilocks zone, where the temperature is just right to sustain liquid water. Go too close, it evaporates. Go too far, it freezes. So it has blown the lid off of any previous very constrained ideas we had about how you might make a solar system. And we've just confirmed that, was it Kepler 90? Kepler's the name of the telescope that made so many of these discoveries. It's found a star system with 8 planets in it. And then we've got 8 planets. Get over the fact that Pluto's not in that list. Just get over it. We have 8 planets. So we're not even the biggest star system around anymore. So I delight in it.
Okay, now, Stephen Hawking, my colleague, wants to build a starship. is the size of a postage stamp. It is propelled by a huge bank of laser beams, and it could reach Proxima Centauri in 20 years or so. So what are your thoughts about one day perhaps venturing to the stars?
Okay, so I think you're talking about Project Starshot, which is highly ambitious. It's what's interesting. It's ambitious in a different way than you'd normally think. Normally, when we think of ambition, as, oh, will there be a ship big enough, and how are we going to go into suspended animation, or how are we going to feed ourselves? They're saying no. We're sending a postage stamp computer that will have a video camera and telemetry and radar and all these things, that some of which are not yet miniaturized to that level yet, but I give it to them. I say, all right, it's a little bit of a fantasy project, but it's also very real. And you propel it with lasers to accelerate them to a fourth the speed of light. And that way it gets there in the 20 years that you say, which is in our lifetimes. Somebody's got to do that. Let them do it, by all means. But still, I don't know if that's an adequate substitute for me going. I want to see Alpha Centauri, and not just have a camera that visits it, because I have telescopes to bring me a little closer visually. So I kind of want to go there myself, and that's why I'm still waiting on the Starship Enterprise and warp drives.
Now, the Webb Space Telescope is going to replace the Hubble. Some people think that it may be big enough to begin to actually photograph some of these exoplanets. Well, tell us a little bit about the Webb Space Telescope.
Yeah, so this telescope will be the most powerful telescope like there ever was. It's being tuned, because you can tune telescopes to be very good in certain parts of the electromagnetic spectrum. And this telescope is tuned to be particularly sensitive to galaxies forming at the beginning of the universe. This was a very big sort of design consideration for the telescope. And this telescope's been on the design table for years, and only now are we nearing its launch. It's end of 2019.
We're going to have to take another short commercial break, but after that, we're going to talk about death by black holes. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest is Dr. Neil deGrasse Tyson, director of the Hayden Planetarium, author of a number of great books, including Astrophysics for People in a Hurry and Death by Black Hole. So first of all, Neil, tell us, what is a black hole?
Well, what's fascinating is Einstein's equation for general relativity, which was the prescription for how the fabric of space and time distort in the presence of matter and energy. He could have used his own equation to predict the existence of black holes, but he just didn't. And I asked Stephen Hawking this, why didn't he? He said, and Stephen Hawking bluntly answered, you can't think of everything. So I thought that was a good answer. And so black holes would be developed later, and we would learn how we might detect them astrophysically in the 1960s and 1970s. Then we started looking. And then we started finding exactly what a black hole would be if it were dining on a star that wandered too close. Because a black hole is black, nothing comes out of it. It is the end stage of the death. One version of a black hole is the end stage of the death of a high mass star. The star implodes at the end of its life when it runs out of fuel. And the surface gravity gets so high that to escape the place, the speed of light is not even fast enough to accomplish this. And so it blips out from your visual existence. And you only really know it's there by the distortion of the pattern of stars behind it, because it's distorting the fabric of space and time, or by material that is spiraling down into it as it flays a star that comes too close, because that becomes highly radiative just before it sinks into the middle. So anytime you hear someone say, we have detected a black hole, they've detected stuff falling into a black hole before it goes beyond the event horizon. So you want to avoid these, because there's no coming back. But we're pretty sure not only are black holes relatively common in a galaxy, we think each galaxy has a supermassive black hole in its dead center. And that's a stunning fact. Every galaxy we've had a good enough data to even ask the question has revealed a supermassive black hole lurking there. So this is we're trying to understand how galaxies are formed. Did the black hole form first and the stars gather later? Did it all form together? Many of these are open questions on the frontier of astrophysics.
You know, I've actually looked into the question of why Einstein missed the black hole in 1916. The reason is, in 1916, people thought that stars were formed by slow condensation. And you can show conclusively that Newton's laws of motion do not allow condensation to give you a black hole. But then J. Robert Oppenheimer, who later built the atomic bomb, talked about implosion, which is an entirely new mechanism that people did not consider back in 1916. And Oppenheimer then used the implosion mechanism not only to drive a black hole, but also the Nagasaki bomb. So the Nagasaki bomb, in some sense, is a child of the black hole.
I did not know that. Interesting. Mm-hmm.
Yeah. Now, let me ask you a question that every child asks, and that is, what happens if you fall through the black hole? Any thoughts?
Yeah, well, if it's a black hole just sitting there minding its own business and you fall feet first, it's unpleasant, really. Well, it's okay initially, and you get a close look at a black hole and you tell all your friends about it. You take pictures, put it on Instagram, and then what happens is that your size relative to a black hole, because black holes are small, your size is larger compared to the black hole than you are compared to Earth. And what that means, well, let me back up. Earth is pulling on your feet more strongly than it's pulling on your head. But that difference is not large enough for you to notice. As you fall towards a black hole, that difference between your feet and head grows and gets bigger and bigger and bigger. And that difference is so great that you begin to stretch. And you stretch beyond the capacity of your molecules to contain you. Then you snap into two pieces, likely at the base of your spine. And then those two pieces continue to feel this tidal force of stretching, and then they snap into two pieces. So you go from 1 to 2 to 4 to 8 to 16 as you bifurcate your way all the way down to this abyss. And that's not even the worst of it. It's the fabric of space and time narrows so that you are actually funneling through an ever narrower channel through space and time, like toothpaste through a tube. And this is where we get the term spaghettification. There's a whole word just to describe how you die while descending into a black hole, which I think is one of the most specific words ever invented.
Now, the next question is, what happens if you fall through the black hole? Is there another side to the black hole, or does it just end?
Well, so that's a great question. So the simple, naive answer is you get compressed down to the center of the singularity and never to return again. But if you look at the equations of the inside of a black hole, they're extraordinary. They actually predict an entire other space-time inside the black hole. And that's, it's spooky and kind of weirdly beautiful that you might fall through the black hole. And by the way, your time changes. So relativity prescribes that the universe will unfold, the future history of the universe will unfold before your eyes as you just fall into the black hole. We, looking at you, looks like you're just stopped.
We have run out of time. However, I suggest you all pick up a copy of his book, Death by Black Hole and Astrophysics for People in a Hurry. So, Neil, thank you so much.
Always good to be with you, Michio.
Okay, very good. So once again, our special guest was, many people believe, is the successor to Carl Sagan, the host of the National Geographic series called Cosmos. And you've been listening to Science Fantastic with Professor Michio Kaku.